The objective of this video is to review basic operational parameters of electromechanical power conversion. Specifically, we're going to be targeting two things. The first is that we're going to talk about the relationship between mechanical shaft power and electromagnetic torque and rotational speed. And the second is that we're going to be talking about the relationship between shaft speed or rotor speed and electric frequency. Suppose you have the following shaft, and it's rotating about its axis in the counterclockwise direction, and there's a torque. Torque for our class is in units of Newton meters, and we define it so that it is positive when it is acting in the counterclockwise direction. And we refer to the speed of our shaft, the rotational speed of our shaft, as the mechanical speed to differentiate it from electrical speed or electrical frequency, which pertains to our voltages and currents. So this shaft has a mechanical speed, and the units for mechanical speed is in radians per second. And we can talk about the shaft's position as being theta, and so our mechanical speed is equal to d theta dt. So the definition of power is that it is the time derivative of energy, and we know from Newtonian physics that we can relate the energy that we are imparting in a physical system as being a force that we're applying to move an object a certain length. And so in our mechanical system, we have a shaft. So when we are imparting a force, it's always a force at the surface of our shaft, and it's to rotate our shaft some angle, theta. And our shaft has a certain radius. So in our system, we can say that the length, which is this out here, this is length, is equal to r times theta. And you should recognize this expression right here as just being torque. Torque is equal to force times the radius that is applied on when it is tangential to the radius. So torque is going to equal to force times radius. And we finally get that power is equal to torque times our mechanical speed. And this is hopefully something that you're already familiar with. For us, power is positive when we're behaving like a motor. That is, we're transferring energy from its electric form. We're transferring energy from electricity into mechanical. Electric power to mechanical power is motor operation, and it's negative when we're converting from mechanical power to electric power. So positive power means that the torque and our rotational speed are in the same direction, whereas negative power or generation is when we're applying torque in the opposite direction as our mechanical speed. That was number one. The second thing we're going to do today is talk about frequency. And so again, I'm going to start by sketching a shaft. And this time on the shaft, I'm going to mount some permanent magnets. And so I'm going to sketch this as a 3D cross-section above, and then I'll sketch a 2D cross-section below. The 3D sketch is going to be a little bit difficult to look at because it's hard to draw in 3D, but I hope that you can get what I'm after here. So I'm mounting this permanent magnet on the surface of our shaft. This would be, for example, a permanent magnet machine, a surface mount permanent magnet machine. And so you can imagine that the magnet has a certain direction. That's the direction that the magnetic field comes out of it. And so we'll say that it's coming out away from the shaft, and that would be called a north pole. And on the opposite side of the shaft, we'll draw a south pole. And so if we were to sketch this down below as just a 2D cross-section, I might draw something like this. And we can say that this rotor, has two poles, or the nomenclature that we'll use in this class is that lowercase p is equal to 1. That means that we have one pole pair. And so you can see that this is two poles because, well, you can count them. We have one pole over here, and we have a second pole over there. That's two poles. Or we have one pair of poles, because magnetic poles always come in pairs. And so the task at hand is to determine how to relate the rotational speed, the mechanical speed of our shaft, to the frequencies that we will observe in a coil. And so let's imagine that we've placed a coil outside of this permanent magnet on the stator somewhere. And so I'm trying to draw a 3D coil, which again, bear with me. And so you can see I've drawn two coil sides traveling down axially, and then I'll connect these with an end connection. And so if I go back to my 2D cross section, I might sketch it like this. So we've got two coil sides, and then you can't see it, but at the opposite end of the page there's a return connection, so that we have a total amount of magnetic field that is traveling through this coil. We have a flux that's going through there. And you'll recall from your prior coursework that when you have, so when you rotate this rotor, that amount of flux that's linking the coil is going to vary with time, and you should be able to recall from your previous coursework that creates what's known as a back EMF, or an EMF, electromotive force, in that coil, which is just a voltage. And so you can recall the EMF is equal to negative d psi dt, where psi is our total flux linkage. And we'll talk about these concepts in detail later. And so what I'm going to do here is I'm going to create a graph of the flux that's linking that coil as a function of the rotor's position. And we'll say that we start at 0, and we've got a sinusoidal flux linkage. So we can see that when we rotate our rotor 180 degrees, or pi radians, our flux linkage is going to repeat itself in the negative direction. And when we rotate our rotor 1 full revolution, or 2 pi radians, our conditions will start over again. And then on the right side, we can sketch what our back EMF would look like. And since we have this nice relationship that our rotor's position is equal to the speed times time, we can continue to sketch this in terms of the rotor position. We're assuming that our rotational speed is constant. And we'll get a cosine instead of a sine. Okay, from this we can observe that the electric frequency, the frequency of our voltage, which we denote with a lowercase f, we know that that's equal to 1 divided by the period. And we can relabel the x-axis of our EMF plot in terms of time by just solving for the fact that t is going to be equal to theta over our mechanical speed. And we finally get this expression. We can calculate our electric angular velocity as being 2 pi times f. So this is converting our frequency to radians per second. And we get that we have the same value as a mechanical. So that's nice. We can now repeat this for a rotor with more poles. So that was the case where we have 2 poles, or 1 pole pair. And we can draw this again for the case where we have 4 poles. So we're just going to double this. And in that case, you can see that if we were to graph our flux linkage, it is going to have twice the frequency as it previously had. That is, 1 rotor revolution corresponds to 2 periods of flux linkage of our coil. Right? So if we stand here and we rotate this rotor 1 full revolution, we're going to see this coil is going to link a north pole, and then a south pole, and then a north pole, and then a south pole again. And so by the time we get to 1 complete rotor revolution, we've gone through 2 periods of our rotor flux linkage. And the same is going to be true for a back EMF. You can imagine that I'm drawing perfect sine waves here. So we can now make the observation that our electric period is half of what it used to be, which means that our electric angular speed is now twice the speed of the rotor, of the mechanical speed. And if you spend a little time with this, you can convince yourself of the relationship between the electric angular frequency and the motor's rotational speed in radians per second in terms of the number of pole pairs of the rotor. So we start out with a 2-pole rotor, and then we move to a 4-pole rotor where P is equal to 2. And you can prove to yourself that, in general, the electric frequency is P times the mechanical frequency, where P is the number of pole pairs. And the last thing I want to point out to this is that oftentimes we'll specify our shaft speed in units of revolutions per minute. What do we mean by RPM? Well, RPM stands for revolutions per minute, or sometimes it's just called 1 over a minute. And so I suggest that you get comfortable converting between revolutions per minute and radians per second, because you'll be doing that frequently in the class. So just like electric frequency, we usually talk about hertz. Mechanical shaft speed, we typically talk about it in units of RPM, or revolutions per minute. And this is just a simple unit conversion. So in summary, we've reviewed the basic power, torque, speed, and frequency relationships for electromechanical power conversion. This is largely based on material that you should have seen in prior coursework, but it's nice to review it to set the stage for this class and also to see the nomenclature that we will be using in the class. We specifically talked about how power is related to torque and shaft speed, and we talked about how shaft speed is related to the frequency of the voltage and currents in our motor coils.